Hello and welcome to another mathematics video in which we seek to understand and analyse and solve ordinary differential equations. In this video I've decided to show you how to derive an ordinary differential equation that results in the general solution u equals gamma over h squared plus c cos theta plus epsilon that describes an orbit of a planet. So as planets orbit the sun, in our case in the solar system, as a planet orbits the sun, the orbit can be described by this equation, which I've just read out. Now, how do we get to that equation? Well, we have to do a bit of analysis, and so I'm going to make a start and show you how we derive this equation of an ellipse, of an elliptical orbit, which is, by the way, a conic or conic section. Now, let's go to section 4, and we can start to draw a diagram. So we first of all draw our x, y axes. So x is along the horizontal and y is along the vertical. Now, excuse me a minute. Yeah. So if 0 is the center of the orbit and a radial vector r joins the center of an orbit to a planet traveling around that center, then we note that there are some other components that need adding in here. So this planet, which we'll call P for planet, it has a radial component. I'm going to draw that probably in red. Let's just change to red. So that has a radial component pointing outwards, which we'll call r hat. This is a unit vector. So if you're familiar with unit vectors, you should be all right with this. So it has a unit radial vector pointing outwards and perpendicular to the motion. Well, perpendicular to the radial vector, I should say. It's not necessarily perpendicular to the motion. In fact, the planet is sort of describing that kind of motion. So in actual fact, what we've got here is a transverse motion, which is described by unit vector theta hat. Now, first of all, I might be sort of taking the cart before the horse here, because what I haven't said is that this angle is theta. So we've got a planet that's joined by a radial vector that makes an angle theta with the horizontal x, and the planet, as it rotates, has a radial unit vector pointing outwards and a transverse unit vector pointing tangentially, which is basically tangent to the orbit at that point. Now, we have to derive some expressions from this basic diagram that we've drawn here. So let me just use my pointer here. Now, we're going to draw in a few more, we're going to add a few more notes to this diagram here. We're going to write a few more things in. So what I'm going to do is I'll just change. Oh, I think we'll stick with blue. We'll stick with blue for now. So if we draw a horizontal component out here like this, that's not perfectly horizontal, is it? So along here is our horizontal component. That's parallel with the x-axis. So we know that that angle is theta there. And we know that resolving, eventually we are going to resolve vertically and horizontally. So let me see if I can get that looking more straight. So we've got this vertical component here, and by symmetry you can work out that if that's theta, this must be 90 minus theta here, and so this must be theta, because that's 90 minus theta there. So that's what that is. So anyway, we don't really need this written in there. It just overcomplicates the diagram, and for some reason that little bit of blue won't disappear. But anyway, never mind. So first of all, we want to work out our radial component. So the radial component in terms of the unit vectors is well, r hat is equal to, well, it's equal to a horizontal component. We'll draw this in green. R hat has a horizontal component along here, and that is just cos theta. So I'm writing that in green there anyway, so at least you know. And r hat also has a vertical component like that, and that is going to be sine theta. Okay, now we've also got to consider this component, the theta hat component. So we'll just write that in. So theta hat is equal to, we'll write in, oh, shall we stick to red for this? Let me see, what shall I choose? No, we'll stick with green, and then we know where we are. I'm not great at, you know, changing from one colour to the next. I find it a bit confusing, but it's good because it does highlight more important things that you'd rather talk about and not get confused with other things. So anyway, theta hat, well, if you look at the vertical, well, if you look at the horizontal component, maybe we should change to orange for this. So for theta hat, there's a green component up there, just like there was for the r hat component, but there's also a horizontal component along here. So the horizontal component comes first, and I'm going to stick with the orange pen for this because that's the horizontal component, which is theta hat sine theta. And actually, I've got that wrong. It's minus theta hat sine theta, or minus sine theta. So let's go ahead and write it in before I get more tongue-tied. So theta hat has, along the horizontal component, a unit coordinate of minus sine theta. And along the vertical, and I'm now writing that in orange, we've got cos theta. So cos theta, if that makes sense. So we've got our two unit vectors, r hat, which is this unit vector resolved horizontally, cos theta, and resolved vertically, sine theta, which you can see here. And then for theta hat, we've got minus sine theta through this angle here, as exemplified in this component of the vector. And then we've got theta, we've got the vertical components of theta hat, which is cos theta, exemplified by this. Now we've got to write down the actual polar form, if you like. Well, we've got to write down what this radial vector is, and I think you would say in polar form. So r, the radial vector r, which is, let me use this pointer so that you can see to what I'm referring. So this radial vector r, which I've underlined as a vector there, is equal to r, so the magnitude of this radial vector is r, just r like that. So that's the magnitude of it. So r can be resolved horizontally, so we get r cos theta, and then we can resolve it vertically to get r sine theta. We'll just write it like we did above, so that we have r cos theta plus r sine theta, right? So that's the polar nature of that radial vector. And in actual fact, we can see that this is equal to r. Let me make that look more like a convincing r is equal to r times r hat. Why is that equal to r times r hat? Because, and I'll just outline this, this component here is the same as this component, and that is r hat, as it shows here. So we'll just delete all of that and leave our equation in this form. So we'll call that equation 1. Let's change back to black ink, try and be a little more consistent. So that's equation 1. I could have labeled these equations as well, which I haven't done, but we'll hopefully manage. Now the next thing to do is to differentiate equation 1, right? So if we differentiate equation 1, we get r, so the radial vector gets differentiated to give r dot. And then we differentiate this. So we differentiate this next and leave that alone, which of course we've written like this. So we differentiate the r and leave the r hat alone. And what we get is, let me just get this pen correctly held. So we've got r dot r hat plus, and then we leave the r alone, and we differentiate the r hat. So dr hat by dt. And we've got to try and simplify this expression. So this, I don't know how to write it. So let's call this, let's call this equation 2. Equation 2, right? So let me just go to section 5. So we've got r dot equal to r dot r hat plus r dr hat by dt. But we know that r hat is equal to cos theta and sine theta. Actually, like cos theta plus sine theta as a unit vector. So if we differentiate this, we get dr hat by dt equal to minus, whoops, I made a mistake, minus sine theta, we'll just close that up there, and this sine theta goes to cos theta. And then what you need to do, and this is very important, you need to differentiate the theta in both cases, so that what we get outside the brackets is theta dot, right? So dr hat by dt is equal to this vector times theta dot. Now, this vector can be written as something else. Let's just go back, because I think it's important that you see this written on the previous sheet. Well, theta hat is equal to minus sine theta cos theta, isn't it? So if we, well, I'll just cut and paste that, Control C, and we'll go back to section 5. So if we just erase that and cut and paste that, let's move that over there. So, but theta hat is equal to minus sine theta over, well, not over, but minus sine theta plus cos theta, if you like. But we've written it as a vector, which is all that is. Then dr hat by dt is equal to theta hat times theta dot. So we've just substituted this theta hat into there, right? So over here we've got r dot is, well, the vector r dot is equal to r dot times r hat plus r theta dot theta hat. Right, okay. So we've got what I will call, I can't remember what equation we got up to, so let me just see where we got up to. So we've got two equations there, and we want to go back to section 5, and when I can find my nib, we'll call this equation 3. Right, so there we've got equation 3. So that's an important equation. And I can't draw straight lines at all on these things. So that's equation 3. Now, we need to differentiate this again. And by the way, we're differentiating this because we need ultimately the acceleration, because the acceleration is crucial in terms of the force, which will end up being the central force that holds the planet in orbit. And that's why we're ultimately finding what the acceleration in order to describe the orbit. So that's why we have to differentiate this to find the acceleration. So when we differentiate this again, we get r double dot equal to, well, we've got an r dot, which I'll leave alone, r dot times dr hat by dt plus r double dot r hat. I'm going to make that look more like a double dot, It doesn't look very, I don't know, that isn't working. Let's just R double dot, right, R hat. So that's that bit differentiated there. And then let's just cordon all of that off. So now we differentiate this using the product rule. So what we get is plus R dot theta dot theta hat. So we've differentiated the R, leaving these two alone. And then we differentiate the theta dot, leaving the R and the theta hat alone. So we get R theta double dot theta hat. And let me just check my notes. So let me just go back and just make sure that I've got this correct. So we're differentiating this by the product rule, and it's important that we get this right. So we've got plus, we'll leave that R alone and differentiate the theta dot and leave the theta hat alone. So we've got R theta double dot theta hat plus R theta dot d theta hat by dt plus theta dot theta hat times dr by dt. So we've differentiated all of this by the product rule to get this, right? And we need to now tidy it up a little. So we know what dr by dt is. Dr by dt is this. But we also, in fact, that's dr hat by dt. So we need to figure out what d theta hat by dt is. Well, that shouldn't be too difficult, because if we just differentiate this theta hat over here, so differentiate this, we get, let's put, and d theta hat by dt is equal to minus cos theta. So that minus sine theta differentiates to give minus cos theta, and the cos theta differentiates to give minus sine theta in brackets. So we could have written it like that, but I'm going to simplify it by writing the minus sign outside the brackets. So we've got cos theta and sine theta. What else do we have outside the brackets? Well, we have to differentiate this theta. Okay, so we get theta dot. And what is what is this vector here? This vector, cos theta sine theta, is nothing more than r hat, right? So this d theta hat by dt is equal to minus r hat theta dot, right? So what we've got over here is r double dot, that's the vector r double dot, is equal to r dot, so like the magnitude, kind of the derivative of the magnitude of the radial vector, times dr hat by dt. Well, we know that's this here. So we'll just substitute that in. And we've got r dot, where's my pointer? Theta dot theta hat. I should really have underlined that for a vector. Plus r double dot r hat. That's this component here. Plus r theta double dot theta hat. R theta double dot theta hat. I'm going to check my notes to make sure that I haven't made any mistakes, and so far it looks okay. And then we have to deal with this component here, so I'll just delete that so it doesn't look too untidy. So we've got plus r theta dot times, in brackets, d theta hat by dt, but we know that d theta hat by dt is minus r hat theta dot. So what we get here is, when I can get my pen lined up, is minus r hat theta dot, and then plus this bit here, which is just simply written as r dot theta hat. And I'm going to double check my work again. Let me see. So we've got r dot theta dot here. Let me use the cursor. R dot theta hat plus r double dot r hat plus r theta double dot theta hat minus, well, this is going to simplify to r squared, to r theta dot squared theta hat, which we'll do in a minute. I've sort of jumped the gun a little bit, plus r dot theta hat. So let me just cut and paste. So we'll just cut and paste that. Oh, let me just start again. Right. So if we bring that, okay, Control X, Control Z. Now we want to go on to a new section. So if I maximize that page, and we'll cut and paste that there. So that's what we've got, right? So this simplifies to give r double dot equal to r dot theta hat plus r double dot r hat. I should really underline these vectors where they are vectors, plus r theta double dot theta hat minus r theta dot squared r hat. So that's that little bit there, and then plus the last bit. That should look more like a plus, and that should look more like a hat. So we've got r dot theta dot, and what is that? Is that a theta hat? I think that should be a theta hat. Let's just go back and see why that didn't have a hat on it. So that should have had a hat. Yeah, I'd even checked it. So you heard me check it, and I still didn't see that I'd made a mistake there. Anyway, never mind. That's what you get being dyslexic. So now we've got an acceleration vector here, and we have to simplify it. So first of all, I'm going to make that look more like a hat. Oh, there we are. I think I've done it. I think I did that by accident. So, okay, let's just make it look a bit more convincing as that. Right. Okay, so we can rewrite this. Rewrite as r double dot equal to, well, it's all right saying rewrite it, but rewrite it as what? Now, we need to recognize that this and this are the radial components, okay? So I'll write that down in orange. So we've got r double dot, r hat, minus r theta dot squared, r hat. And then I'm going to change to a nice green colour. I think green looks quite nice. So the transverse components are these, right? And also, you'll notice that this and this can be added together to give plus 2r dot theta hat plus r theta double dot theta hat. There, so that's plus that third one there. So this can be rewritten as r double dot equal to r double dot minus r theta dot squared. Put brackets round r hat plus 2r dot theta dot, and I'm making sure that I haven't made any mistakes as best I can, plus r theta double dot, and that's multiplied by a theta hat. So that really should have a line underneath it. So we're getting closer to what we want to achieve now. This term here can be rewritten as, well, let's write the whole thing out again. So we've got r double dot minus r theta dot squared, r hat, plus, well, how can we rewrite this bit that I've underlined? Let me just scroll down a little bit. So this can be rewritten as 1 over r. So let me just highlight this with the cursor. This here can be rewritten as 1 over r times d. It would be nice if that looked more like a d, wouldn't it? D by dt of r squared theta dot theta hat. Now I'll just convince you, if you need convincing, that all of this is equal to all of this. Right, so basically it's just a trick, a kind of a trick, but it's a legitimate trick, where if we've got 1 over r, let's just section this off. 1 over r d by dt of r squared theta dot, we'll put the theta hat in there because I'll probably forget about it if I don't. By the way, I should have really underlined that. So we've got 1 over r times, well, we differentiate the r squared first to get 2r, and there's a theta dot there, and then we just differentiating using product rules. So 2r theta dot plus, well, this time we leave the r squared alone, and we differentiate the theta dot to get theta double dot. We don't need to differentiate theta again there. because this is already a theta is already a function of time, so we don't need to do that, and therefore we have theta hat. And I think what have I? There's something. Oh, right. Yeah, that's it. I've made a mistake. So let's just go back a bit. Sorry about this. We'll start again with the differentiation via the product rule. So we've got, we differentiate the r squared, leaving the theta dot alone. All right. So we get 2r, and then we have to differentiate the r again. So it's r dot, and we'll leave the theta dot alone, plus r squared theta double dot. So we've differentiated the theta dot, leaving the r squared alone, and that's multiplied by theta hat. All right. So this simplifies to give, in brackets, 2r dot theta dot, I hope, I do make mistakes, plus r theta double dot theta hat. And sorry about the errors and the mistakes. Hopefully this will make sense to you. So you can therefore verify that this equals this equals this, right? So therefore we can write this as this. Okay. Now this equation, which I'm going to call equation 4, has actually got two components. One of them is 0. The reason is this. Now, this is the radial acceleration, but this is the transverse component. Now, the transverse component is 0 along the radial vector. This is to do with the conservation of angular acceleration. This has to be equal to 0, because if it wasn't, it would change the angular acceleration, which is all of this really. So if angular acceleration was not conserved, then this would not be equal to 0. It would be equal to something that would affect the angular acceleration, but angular acceleration has always got to be conserved, so it can't change as such. So therefore, let's move down. So how shall I write this? Equation 4 is the radial acceleration in which 1 over r d by dt of r squared theta dot theta hat is equal to 0. So for the reasons that I've already specified. Oh, and by the way, let's just go on to a different page. So where are there we are. So I want to cut and paste this, right? Control C, and we'll go now to a new section and cut and paste that. Right, okay. So ignore these little curly brackets here. I obviously couldn't get rid of those. Yeah, so we know that this is the radial acceleration. So the radial force F of R, R hat, is equal to m. You just multiply all of this by m to get the force, as I'm doing now, plus 1 over, oh, that would be m over r d by dt of r squared theta dot theta hat. Right, okay. So that is the radial force. And because, as I've said, because this component is equal to 0, then we can write two things. We can write the kind of resulting radial force as f of r. We should really have a r hat in there, an r hat, and that's equal to m r double dot minus r theta dot squared r hat on its own. So we can therefore write f of r. My writing is getting worse and worse and worse, isn't it? So f of r equal to m r double dot minus r theta dot squared, just like that. And we'll call this equation 5. And we've got m over r d by dt of r squared theta dot theta hat equal to 0. So therefore d by dt of r squared theta dot is equal to 0. And if you integrate both sides of this, you find that r squared theta dot is equal to a constant, which we call h. You might be familiar with that. That is the rate of change of angular momentum is a constant. Is that right? Anyway, so that's equal to a constant. Do check some of the things I say. So because r squared theta dot is equal to h, we'll call that equation 6. Then theta dot is equal to h over r squared, right? So we'll call this equation 7. So f of r is equal to m r double dot minus r, well, it's theta dot squared. So over here, theta dot squared will be equal to h squared over r to the 4, wouldn't it? So this would be equation 8. 6, 7, and 8. Well, I can't draw my arrow heads very sufficiently. Right, so we've got theta dot squared equals h squared over r to the power 4. So this becomes r times h squared over r to the 4. And this simplifies further to f of r equal to m times r double dot minus h squared over r cubed, right? And that's a really important equation, equation 9. So when we're sort of getting towards where we want to be now, because what this says is that the radial force is equal to the mass times the radial acceleration component, which is this in equation 9. Now, let's go on to a new section, section 8. So we've established, I'll just write this down again. So we have established that the radial force F of R is equal to M times R double dot minus 8 squared over R cubed, right? Now, it's well known in physics and applied mathematics that R is proportional to the velocity u, inversely proportional, I should say. So R is inversely proportional to the velocity. And actually, what we find is that I'll write this down. Actually, R is equal to 1 over u. So it's inversely proportional to the velocity. And in this particular case, the probably because it's in astronomical units or something like that, the constant of proportionality that would normally go here like that, that is 1. Usually in physics, you find physicists, particularly and applied mathematicians, like to equate constants like this to unity. They like to equate things to 1 or unity where they can. So I'll just scrub that out for now because I've explained that. So we want to now use this fact in order to derive the acceleration from this here, to derive the acceleration from this and substitute it back into there. Now, I think I said that this was equation 9, didn't I? I ought to check that. Question 7, or section 7. Yeah, so that was equation 9, right? So we'll call this equation 10. So from equation 10, R dot is equal to d by dt of 1 over u, which is equal to minus 1 over u squared d u by dt. Okay. Now we know, since we know from equation, and let me just check which equation that is. I might not have even given it a number. Let's just have a look here. Did I? Oh, there we are. A little bit slow to respond. Let me just get the right. Okay. So, yeah. So in equation 6, we've got r squared theta dot equals h, right? So from equation 6, we have r squared theta dot equal to h. Is that actually what I found? R squared theta dot is equal to h. Therefore, this can be rewritten as 1 over u squared theta dot equal to 8. Why is that? Well, we know, as we said up here, r is equal to 1 over u. R is equal to 1 over u. So if we put r equal to 1 over u in here, we get 1 over u squared theta dot equal to h. So this implies that theta dot is equal to HU squared, right? And I'm sure I'm probably, what have I got here? Theta dot is equal to HU squared, therefore R dot equals, well, we know that R dot is equal to minus 1 over U squared du by dt. But this can be rewritten as minus 1 over U squared du by d theta times d theta by dt. So we've gone from here, we'll call this equation, I wish I could draw my lines straight, I really wish. So that's equation 11. So we've gone from equation 11 to equation 12. So R dot is now equal to minus 1 over U squared. Let's make that look clearer. Minus 1 over U squared times theta dot times du by d theta. And we know what theta dot is because I've just highlighted it here. Theta dot is equal to HU squared. So we've got R dot is equal to minus 1 over U squared times theta dot, I'll write it in green, times HU squared, suppose I have to put brackets around that, times du by d theta, right? And that comes out to be equal to minus h du by d theta. And we'll call that equation 13. So R dot, let's move on to, well, we can probably scroll down a little bit, can't we? Therefore, I'll write it more clearly. R dot is equal to minus h du by d theta. So R double dot is equal to minus h d by dt of du by d theta, which can be rewritten again as minus h d by d theta times du by d theta times, because we're using the chain rule again, so what we used up here, where you can see the cursor moving around in equation 12, we used the chain rule because we wanted to get the equation in terms of theta, the angle being swept out, rather than the time. And so we're using the chain rule down here again. And so if we introduce a d theta down here, we have to move the dt, when I can find my pen nib, there it is, dt, and then a d theta up there, which is the same as minus h theta dot d squared u by d theta squared. So you see that bit there is this bit here, d squared u by d theta squared, and this is our theta dot, which is here. Okay, it's quite intricate. I wouldn't say it was overly difficult, but it can be very confusing, and it can be difficult to understand if it's not explained properly. So we'll go on to the next. We'll go on to the next page. But let me just, yeah. So we'll go on to the next page. So we've got, we've discovered that R double dot is equal to, and I have to look back at it now because I can't remember. I cannot remember what I've written down. So let's just cut and paste this. I'm getting used to this new software, and I'm constantly trying to find software that's easier to use. Now, what was I doing? Right, so that's what I want to cut and paste. Control C. And we go back to section 9 and we'll just drop it there. Drop it there. How about there? Control V. Right. Let's just. Right. Okay. So R double dot is equal to that. But we know that R squared theta dot is equal to H. Do you remember? This is equation 6 from equation 6, I think it was. I'm going to just leave that as it is. I think it was equation 6. So therefore, theta dot equals H over R squared, but we know that R is inversely proportional to U. So that's equal to H U squared. So therefore, R double dot is equal to minus H times H U squared D squared U by D theta squared. Okay, so therefore R double dot is equal to minus H squared U squared D squared U by D theta squared. Now, we're nearly there. We're on just another couple of so equations and we'll be finished. So I've got to go back and find the equation, though, into which we have to substitute that. So let me, I think it's in this section here. So, yeah. So equation 9. So let's just cut and paste that. That's it. Control C. Section 9. Maximize. Let me go down a bit. Let's cut and paste it there. So just a minute. That's it. Okay. Right. So that should be f of r is equal to that. So now let me just go back once again. I do hope you've got patience with me. Many apologies for all the any incoherences. So we're calling that equation 16, right? So that's equation 16. So we'll relabel this here as equation 16. Let's just maximize the screen. So 16 can be so actually equation 9. So equation 9 can be rewritten as right, let's just make a bit more space over here. So I said that was equation 16. Let's go right to the top, right, We'll put a line down here like so, and if we substitute the right hand side of equation 16 into equation 9, we get let me see, f of well, we know that f of r is equal to m times r double dot minus h squared over r cubed, right? So we've just written that down. That's equation 9, which I'm going to write here again. Now we know that r double dot is the right hand side of equation 16. So f of 1 over u, because this is where we substitute 1 over u in for r, is equal to m times minus h squared u squared d squared u by d theta squared. There we are. Minus h squared u cubed. Do you see where that u cubed comes from? R is equal to 1 over u. So if you substitute 1 over u into 1 over r cubed, you get u cubed. Okay? So for a planet whose force due to gravitation is f of r equal to g big M little m over r squared, or if you like, f of 1 over u equal to g big M little m u squared. So again, we're substituting r equals 1 over u. Remember that to get this. So I'll just get rid of that. And in fact, actually, I've missed something out. Let's just write in the fact that that's negative. So that force due to gravitation, the gravitational force is negative. Hence, we have, and I'm going to go on to the next page now because I really can't cram that in. So, since f of 1 over u is equal to m times minus h squared u squared d squared u by d theta squared minus h squared u cubed, and f of 1 over u equals g minus gm little m u squared, then we have finally m times minus h squared u squared d squared u by d theta squared minus h squared u cubed equal to minus gm little m u squared, and the m's cancel, and in fact the u's effectively cancel, leaving one u there. That u squared cancels, let me go back. I didn't want that to happen. Right, okay. Then so we're left with h squared d squared u by d theta squared minus h squared u equal to minus g m, like that. In fact, actually, everything's positive, isn't it? Because if that's negative, so I'll point with the cursor. If that's negative, and that's negative, and that's negative, if you multiply both sides of the equation by -1, then everything becomes positive. Now, this equation, and I can't remember what equation labels we got up to. Let's just have a look. So we got up to equation 16, didn't we? Okay, we got up to equation 16. So we'll call this equation 17. Equation 17. This can be simplified to give d squared u by d theta squared plus u equals gamma over h squared. What is gamma? Well, gamma equals gm. And we'll call that equation 18. Now, those of you who have done A-levels, high school mathematics, advanced high school mathematics, will recognise immediately what this left-hand side represents, and indeed what the whole equation represents. And this is simple harmonic motion. So in other words, it's periodic. So it's periodic motion. So we can infer from this that let's just get back to black ink. Thus, can I just delete all of that, because we've established that it's periodic. So therefore, the planet is going round the sun in a periodic sort of circular elliptic motion, and the solution to this equation is, I'll put the general solution to 18 is u equals a cos theta plus b sine theta plus gamma over h squared. If you have done basic basic second order linear differential equations of this type here, this is a non-homogeneous or inhomogeneous second order simple harmonic motion equation. If you've learned how to solve equations like that, you'll easily be able to write down this solution, which can also be written as u equals gamma over h squared plus c. I'm going to call it c1, then it doesn't mix up with the c of the cosine term. We don't want two c's together, really, you know. So we've got gamma over h squared plus c1 cos of theta plus epsilon, and that is the final general solution to a planet's elliptic motion about a star, any star really, that anywhere in the universe. So that's just about that. You can go further, and you if you're given particular initial conditions, you can work out the specifics of the orbit, and things get quite complicated when proceeding from this solution here to try and find the period, but you will find that I think you get Kepler's third law. Is it Kepler's third law where I can't remember it in detail, but you get a relationship between the period and the radial distance. I can't remember how that goes now. It's something like t squared is equal to k r cubed, or maybe it's what is it? I don't think it's t cubed equals to k r squared. I suspect it's this one here. But if you go further with in all sorts of initial conditions and do further really complex analysis, you will arrive at that law of Kepler. So I hope you've enjoyed that video, and I hope you've got something out of it. I don't know how many more videos on YouTube are like this on this specific thing, but I hope that in your searching you've come across this video and that it has helped you. So until next time, I'll bid you farewell, but I'll hopefully see you later. Okay, take care then. Bye.